I am going to do these videos all in one shot, so I don't really want to make two separate ones, and I'm also using my notes, so sue me if you want. Okay, I'm going to go over autorhythmic cells, cardiomyocytes, how they work. I'm going to go over EKGs and why they look like what they do. I'm going to go over things called STEMIs and NSTEMIs, which is basically damage to the heart. I'm going to go over contraction of the ventricles, pressure, and then sounds of the heart. I'm also going to go over the isovolumic lines, as well as I don't know what that loop is called, the contraction loop, and then changing afterload and preload. I'm also going to go over pressure, baroreceptors, the RAA system. I'm going to talk about capillary exchange, which is actually interesting. And then I'm also going to go over blood a little bit. I think this is all that's in these two videos. I think it's exam 3, essay 1 and 2, but I could be wrong. But that's what I'm going to go over in this video, so it's going to be kind of a long one. Bear with me. All right. So first, you have two types of cells in your heart. You have autorhythmic, and then these cells are found in the SA node and the AV node. And then you also have something called a cardiomyocyte, which is exactly what it sounds like. It is a cell that's in your heart muscle. So it's just everywhere other than the pacemaker cells, or everywhere where there's not really electroconductivity happening. And so there's two different graphs for both of these kinds of cells, and they look a little bit different. And so I'm going to start with the autorhythmic, and then I'll explain cardiomyocyte. So autorhythmic cells are super unique because they're very, very specialized. And so their graphs kind of look like, just like here's threshold, and then like here's where it repeats, obviously. It's very interesting because it doesn't have any sodium channels, any voltage gated sodium channels, where everywhere else in the body, it's just everywhere else other than this place. And so what controls the depolarization and repolarization of the autorhythmic cells are the voltage gated calcium channels and voltage gated potassium channels. But what starts the action potential is something called an HCN channel, which is called, I promise I had this before, hyperpolarization cyclic nucleotide, which is also referred to as the funny channel, because when they discovered it, they thought it was funny. So that's how action potentials work in autorhythmic cells. However, cardiomyocytes are a little bit more like what we're used to, and so they sit about -90. That's the resting membrane potential. Here's threshold or whatever. Depolarization starts to happen, an action potential happens. There's a peak, and then there's something we call a plateau, and then it drops off and goes all the way to hyperpolarization and stays there. This is because there is a ton of channels working in these types of cells, in cardiomyocytes, whereas we only had 3 over here. We have a ton over here. So first, obviously, we have the voltage-gated sodium channels that helps depolarize the cell. And at this very top, we have something called an ITO channel, which lets in chloride and potassium. And then all throughout this plateau, we have 3 different types of potassium channels. We have IKUR. I'll go over what the names mean once I'm done labeling this. We have IKR, and then we have IKS. And then during repolarization, we have something called an IK1 channel, which drops it all the way down to hyperpolarization and stays there until the next action potential. What I didn't write down, but is what is basically causing this plateau, is that there's 2 types of calcium channels. So calcium channels, there's a T-type and an L-type. L-type are slower, T-type are faster. And then these names are based on their activation rates. And so they start to be activated when the voltage-gated sodium channels are activated, but they're slower to respond. And so they're open right here at the same time that all of these potassium channels are open, which is what is making that plateau. And so it's just 2 different charges trying to work with each other, and it's just causing a plateau. And so at this point, right here, when we start to repolarize, that's when these calcium channels close, and they're no longer like fighting with the potassium anymore, and then it just plummets all the way to the bottom. And so what these names are is I'm not gonna write them down because they're pretty straightforward. So IKUR is a potassium channel that's ultra rapid. IKR is a potassium channel that's rapid, and then IKS is a slow channel. And so those are talking about their inactivation or like closing rates. And then this I believe is like it puts more potassium in it. And so that's what those guys look like. And so something that's very specialized that's going to come up later in my little video is that these cells, their absolute refractory period make it almost impossible for them to have too many action potentials happening. So when we were looking at muscle cells, they were able to enter into a state of tetany or tetanus, and so they had so many contractions that there wasn't a relaxation period. But these two different types of cells prevent that, and so that's going to come into importance later when I talk about preload and afterload. It'll make a lot more sense because like time is another factor into this. But those are the two different types of cells that are in autorhythmic and cardiomyocytes. Very, very interesting. All right. Next, I'm going to talk about an EKG. And so first, I'm just going to draw what a normal EKG looks like, and then I'll just reference back to this picture. So we have a P wave, we have a QRS complex, and then we have a T wave. And so this is just a visual representation of what action potentials are going where in the heart at what stage. And so when we're looking at P, I'm just going to draw a very simplified heart here. Here is the atrium, here's the ventricles. And so we're only looking at the atrium during the P wave. And so what happens is the SA node sends action potentials towards the AV node. And it'll not necessarily depolarize in stages, but that's why it looks like that. And so when part of the EKG is at its peak, that means that half of whatever system you're talking about is depolarized or repolarized, or just half the action potentials have already happened. And so when the atrium are halfway depolarized, then the P wave is at its peak, and then as it goes to all the way being depolarized, it goes back down. So that's what the P wave looks like. When you talk about the QRS complex, we now move on to the ventricles. And so the ventricles obviously have three different types of vectors. And before I move on, I need to explain what vectors are. So vectors are basically just the average movement of these action potentials. And so when we're looking at like positive and negatives and whatever, and the directions that these vectors are going, we have an electrode, a negative electrode here, a positive electrode here. And so when we are being depolarized, there is negative action potentials moving towards the positive sensor. And so, well, sometimes. That's just like the baseline that I base it off of. I'll explain it as I go, okay? So first, the AV node conducts these vectors to the right and kind of upwards. And so the average vector for the Q wave is going to more towards the negative sensor, but not directly towards it. That's when we get, I'm gonna use the words negative and positive when describing the EKG, but I'm just talking about below baseline or above baseline. And so this is a negative little dip, little scoop, if you will, because it's a negative tail going towards a negative sensor. And so then after this side of the heart is getting depolarized, we move down the interverticular septum and towards the positive center. And so because it's negative again, moving towards the positive center, it's very, very direct in this stage. We're gonna go way positive. So that's the R. And then it needs to go back towards the left side and repolarize that way, and then that causes this negative dip for the S wave. So when we're talking about, so both the P wave and the QRS complex is both describing depolarization. This one is called depolarization of the atrium, and this is depolarization of the ventricles. But the T wave is talking about repolarization of pretty much the ventricles, really. There technically is a wave that describes the repolarization of the atrium. It just gets overshadowed by the huge QRS wave because it's just a lot more energy, a lot more active potentials, so it doesn't really show up on EKGs. But T is, I'm just gonna use this picture also. Hopefully the white, I don't have another color, so hopefully the white doesn't get confusing. But repolarization happens in the opposite direction, and so now, since it's repolarization, it's a positive tail moving towards the negative sensor, so that's why it goes up. Yeah, but that's what a normal EKG looks like. I'm gonna talk about this next section is gonna be talking about abnormal, 3 different types of abnormal EKGs. I mean, there's like tons. There can be so many things wrong with your heart, but I'm just gonna talk about 3 of them. Obviously, you know that. But, so first, I need to get hypoxia out of the way, and so this is your heart. I'm just looking at the left ventricle here. We have vessels that run down the side of it, the coronary arteries, and these guys move from the epicardium into the endocardium. And so when something like a thrombus happens over here, or an embolism or something, or we just have like a decrease in perfusion or anything like that, then it leads to hypoxia, which is the lack of oxygen in these tissues, I guess. And so what's gonna be affected first is the endocardium, because it's the farthest away from the coronary arteries. And so we have on the cardiomyocytes, we have channels that are potassium channels, but they're activated by a decrease in ATP. And so if there's ATP on here, I'm gonna put a lid on it. I don't know if this is what it looks like. Oops. Actually, hold on. So it's closed when ATP is bound to it, but when there's a lack of oxygen, there is a lack of the electron transport chain in mitochondria. Thought I just got that wrong. That'd be so embarrassing. And then there is a lack of ATP. So ATP gets kicked off of this, and then this channel, this potassium channel can open, so then it lets potassium into the cell, which causes an action potential or depolarization. And so, like I said before, hypoxia affects the endocardium first, and as opposed to the epicardium. So when we're looking at the T wave specifically, this is where it's going to be affected when I'm talking about hypoxia. We're going to get repolarization from the endocardium to epicardium, as opposed to when it's normal, it repolarizes from the epicardium to the endocardium. And so then this vector is going down to the positive sensor down here, but it's a positive charge. And so when we see minor hypoxia in the heart, it's going to be an inverted T wave. And so this EKG is going to look normal until we get to the T wave, but it's going to look inverted because of the change in vector. This is the least not least concerning, but least dangerous out of the 3 I'm going to talk about, because that's just like hyperkalemia. Like, you can solve that with medications and digoxin and whatever. But the next 2 I'm going to talk about is when you have like actual heart damage, which is not chill. So again, I'm just going to be drawing the left ventricle. And so when you get extreme, or I guess moderate to extreme hypoxia, you start to get sections of the endocardium that start to die. So this white area that I just colored in is going to represent a part of the endocardium that has been damaged. And so it's not able to transmit electrical impulses anymore. And so this guy is always going to have negatives around him. So when the vector comes through here and makes it positive, it doesn't transmit that electrical information. And so then we have little dipoles, little fields of energy, I guess, which again makes more vectors moving towards the positive sensor. So if I were to draw the EKG of this, I'll draw a normal one for reference. But then all of a sudden, it's just gonna like move to, I'm gonna call this our zebra, or Z 0, it's just gonna move to a new 0 and then have like a cute little regular heartbeat here. But then when we get to the S wave, at the beginning of the S wave needs to go back to the normal 0, but then still, because we have that damaged heart tissue, we still need that T wave. It's gonna go back to our new 0. And so this is what the EKG is gonna look like when we have, this is what is called an NSTEMI. NSTEMI, which stands for a non-ST elevation myocardial infarction. And so this is more concerning than an inverted T wave or hypoxia or hyperkalemia, whatever you want to call that first thing I explained, but it's not as concerning as a STEMI, and so that's why we call it an NSTEMI, so not an elevation. So we would call this an ST depression. That's also what it's referred to as. So the next thing I'm going to explain, the STEMI, is just a more advanced condition, I guess, from an NSTEMI. So an NSTEMI is what turns into a STEMI. And so again, we have the left ventricle, but now we have a transmural infarction. And so a whole section from the endocardium to the epicardium is dead. It is damaged. It cannot transmit that electrical information anymore. And so again, we have these negative charges on this damaged part, but we have these little positives. And so these guys create these little dipoles, the energy fields or whatever, which moves the electrical vector up towards the negative sensor. So whereas during the NSTEMI, the new 0 became more positive, this one is going to become more negative here. However, this R wave needs to go way up, the S wave needs to go back to normal, but then we need to go back down to our new 0 because of the vector. And so that is what an NSTEMI is going to look like, or this is what a STEMI looks like. Or it's also referred to as an ST elevation. So STEMI is an ST elevation myocardial infarction. So this is telling you that there is total and complete heart damage from the endocardium to the epicardium. And you can see that from the EKG, so the change in electrical activity in the heart. Yeah, there's those BTW. Very interesting what information you can get from just measuring electrical impulses. Okay. Again, pretty much for the rest of this time, I'm really going to be referring to the left ventricle because it's going to move blood systemically, which is the most important. I mean, all the other things the heart does is important, but left ventricle is the coolest, I guess. Okay, this next graph, pretty much this whole video is just going to be graphs. The sixth graph, the x-axis I'm not going to draw, but the x-axis is time, and then the y-axis is going to measure pressure in millimeters of mercury, so mmHg. And so first, I am going to talk about the left atrium because it does affect the left ventricle, so I guess I have to write it down. But we have systole, it contracts. We have a little bit of pressure when the ventricles contract, but other than that, doesn't really do much. But again, still important. So when I talk about the left ventricle, I mean, it follows this guy. When there's pressure in the left atrium, it goes up a little bit. But when the left ventricle contracts, I mean, she contracts, okay? And so here, I'm gonna reference a couple of these vocab words later, so I don't remember them, write them down, think about them. Right here, you can see that the pressure is going up, but it's going up very quickly, but the volume is not changing. And so this is called isovolumic, so literally same volume contraction. Because right here is where the lung sound happens, or also known as the AV valves are closed. So all valves at this point and up until what I'm going to talk about next, all the valves are closed. So contraction of the heart is happening, there's just really no movement of blood. And so this dotted line that I'm drawing now is pressure in the aorta, or like in the arteries. So you may be thinking, oh my gosh, at the peak of this little parabola thing we got going on here, that must be where the SL valves open. And you know what? You would actually be wrong. It actually happens here at something called the diacratic notch. So here is where the dove sounds open. So this is where the semilunar valves close. And so if all of the valves are closed once again, we're gonna have isovolumic relaxation. So a lot of this pressure is not talking about the amount of blood that's in your heart, it's just talking about the muscles and how they contract and when they're contracting. And so that's pretty much all for that. And then I'll just draw a simple little graph below it. This is just going to represent the volume of blood in the left ventricle. And so this is going to be our end systolic volume. This is going to be our end systolic volume. So when we do our EDV minus our ESP, that is how we get our stroke volume. This is going to become very important in another graph that I'm going to draw. So also remember that. Hope you're taking notes right now. All right, but that is, I think this is a really good visual as to see the effect that atrium versus ventricles have on blood, and like gives you a great, like a better view on when and where and why pressure happens and when things close and when things open, and so just gives you a better idea of how the heart works. But so does all the other graphs I'm about to draw. There's also different sounds. I'm not going to write them down because it's just a lot of noise. Like it's a lot of noise. But a normal heart rate is going to sound like lub dub, lub dub. And those are the closing. So lub is the closing of the AV valves. The dub is the closing of the semilunar valves. And then any other extra sound, there's obviously something wrong. And so it's either a leaky channel, or not a leaky channel, a leaky valve, or you can have aortic stenosis, which makes it harder for things to open, or it makes the semilunar valves a little bit more leaky. So any other sound is just gonna be like, shh, and you're like, that's not right. And so listen to it and you'll know. Okay, next I'm gonna talk about inotropic lines. So this next graph, you gotta keep in mind that this next graph, remember what the axes are, because it's not time. And so if you think it's time, it's gonna be mad confusing. So the x-axis is gonna be volume in milliliters, like always. And then the y-axis is going to be pressure again, in millimeters of mercury, because what else would you use? And so this is just gonna look like a loop as opposed to a goofy little line or goofy little function. And so when volume increases, pressure increases a little bit, obviously. We're gonna have something that looks like that. I'll draw it and then I'll label it. Something that looks like that, something that looks like that, something that looks like that. This is just a loop on how your blood moves throughout your heart. When valves are moving, it's just another visual representation of how your heart works, basically. Here is where love happens. Here is where dub happens. AV valves are open right here. Semilunar valves are open right here, which obviously would tell you they're closed here and closed here. This line to this line represents stroke volume. So here is end systolic volume and systolic volume. That's stroke volume. Here, where the dub happens, this is where we say this is the max contraction of your ventricles. Yes, oh, and then, like I said before, right here, the volume is staying the same, however, pressure is decreasing. Here, the volume is staying the same, but pressure is increasing. So we have isovolumic relaxation here, isovolumic contraction here. So we're going this way, basically, is what's happening here. However, like I said before, we're gonna use this graph to find an inotropic line. Inotropy is anything that causes the heart to contract more. And so to visually represent the tangent line I'm going to find, we just make a little line to this point of max contraction, and then the change in volume and the change in pressure is gonna make a cute little triangle for us to measure. So I'm just gonna move this over here. And so what we're measuring here, like this inotropic tangent line, is helping us measure something I'm gonna label as E. So anytime I write E, I'm talking about elastance, or like the stiffness of the ventricles. So this is going to equal the change in pressure over the change in volume. So like I said before, it's just a tangent line. We're just finding line. And so if we were to visually represent this, so if we were to use that triangle, it'd look like this. However, if we didn't change as much in volume, this arched triangle, just like visually looking at the triangle, you can kind of see what's up. So here, this triangle would be like more stiff in comparison to this triangle. So this just gives you a visual representation of how hard the heart is contracting and where the volume is going. Because let me show you what happens when you change a couple of things, because what would these graphs mean if it isn't interpretation? Stuff that goes wrong with the heart. It's wild the heart is just works most of the time. Like so many things are happening all of the time, and just it all pretty much goes right, and I think that's wild. Gotta fix my little chalk here. Okay. I'm just gonna draw a simpler graph, but just remember everything I labeled. So I'm gonna draw a normal graph here. I'm gonna add a couple of more labels. So here is what we call preload. Oh, sorry, that was the most annoying noise ever. And then here is what we call afterload. So when I'm talking about preload, I'm talking about a change in volume. And then if I'm talking about afterload, I'm talking about a change in pressure or like contraction. So here is what a normal loop looks like, right? So if I were to increase, I'm gonna use the dotted lines for what I'm changing. If I were to increase preload, I can just go back to my same points, and it's just gonna be a larger loop, but just more volume. So like this would be like you're working out, or your heart's bigger, I don't know. But if I were to, this is just a change in volume. So where I'm just adding more blood. That's pretty much all I'm doing. However, if I change afterload, it's going to, I'm also gonna write here is stroke volume. So here, stroke volume increases. However, here, stroke volume is going to decrease because, like I said before, and you should have noted and remembered, that your heart only has so much time to contract. And so right here, when I'm changing afterload, I'm pretty much increasing the resistance. So your ventricles have to contract harder and longer in order to open those semilunar valves. And so it only has so much time, so it's wasting a lot of time trying to compensate for that change in resistance. Sorry, my nose is so itchy. Oh my gosh, this is so embarrassing. So it's wasting a lot of time trying to get the blood out that it only has so much time to release pressure, and so that's why it changes stroke volume. So if afterload were to increase and stroke volume were to decrease, if we remember cardiac output equals stroke volume times, heart rate. Oh, sorry. So stroke volume is going to go down, so for your body to compensate for the decrease in cardiac output, your heart rate is going to go up. So, yeah, it's just, these graphs can help you understand what's going to change when something goes wrong. So, like using all of these little equations, you can see what needs to change and what, it's just relationships really. Variables and relationships is what we're talking about all throughout this video, and all throughout this unit, and all throughout your heart, and pretty much all throughout your body, and whatever. And so, I mean, if you don't get that checked out, it's a negative feedback loop now because something's going down, and then the reaction is going up. But eventually your heart rate is going to go down, so it's going to become a positive feedback loop. And then you're going to die, but you know, happens to everyone. All right. 1, 2. I have 3 more sections to do, and then we're done, so I'm getting there. All right. Next, I'm going to talk about a couple of equations and how that teaches us about peripheral resistance, and then I'll talk about baroreceptors, and then I'll talk about the RAA system. And so, yo, look, I made another graph. All right, so this next graph is going to be a visual representation, like all of them are, of the pressure in all the vessels in your body in relation to how far away they are from the heart. So here, like this is like in your heart, or like your aorta, and then here is like your veins. So like here's like capillaries, and here would be like arterioles, and so it's just, as it's moving on, the pressure is going to be changing, because you can't put like 90 millimeters of mercury into capillaries. They're too small for that. They would just actually explode and you would die. So, whatever. All right. Again, I'm gonna write MAP. MAP equals cardiac output times peripheral resistance. Cardiac output is your stroke volume times heart rate, and then your stroke volume is your EDV minus your ESV. And so when we look at these new equations, we can see what is really going to change. So this is now explaining peripheral resistance. So I've talked a lot about our cardiac output. I've talked a lot about stroke volume and heart rate and end-systolic volume and systolic volume and everything about the heart. But now I'm going to be talking about peripheral resistance, which is all about vessels, and that's what this graph is about. And it's showing you the different pressures in vessels and stuff. And so I'm just going to erase this for now. That was just a little reminder. And so when I'm talking about peripheral resistance, we can use the equation 8VL over pi R4. I'm going to come back to that. I'm going to come back to this, but for now I'm not going to explain it. But hold on to your horses. Don't cry. Don't scream. It's okay. I'm going to come back to it. We also have a flow rate. I don't like this chalk anymore. Equation. This flow rate equation is going to equal the change in pressure, so delta P, over peripheral resistance. So we can use this guy to find this guy. And then we also have something called, I don't know how to say it, but I'm going to write it out. And you're going to be like, oh my gosh, I know exactly what she's talking about. It's just another equation. And then SU I LLES log. Like everything is just another equation. And then this is delta P pi R4 over 8VL. So a lot of this flow rate you can find, like you just need to find peripheral resistance, but both this law and peripheral resistance, there's a lot of constants, lots of things you can't super change. I mean, like this 8 is always going to be an 8, and this pi is always going to be a pi. But what's going to change the most, and especially it's going to be the most impactful number, is this pi to the 4th and this pi to, or this radius to the 4th, so R4, and this radius to the 4th. All of that is saying is the diameter of your blood vessels. So vasoconstriction and vasodilation are the most important factors when we are talking about peripheral resistance. So things that can cause this are sympathetic stimulation of alpha-1 receptors, but something that can also cause an increase in peripheral resistance is an increase in cholesterol or a thrombus or something blocking these. And so, yes, your body does a lot with vasoconstriction and vasodilation, but it's really what abnormal diameters and abnormal constriction is really what's going to kill your heart. Yeah, that's really all I wanted to say about that. That section is just all about math, so we love her. Okay, baroreceptors are basically your body is using these equations to keep MAP constant because we're trying to keep homeostasis. So we want to keep MAP the same. So if something is going to decrease, we want to increase the other thing because it's just a lot of multiplication. And so here's your heart. Obviously, we have your aorta, we have your 3 branches, and then we have something called the carotid sinus. That again doesn't matter. So on your aorta, you have, and on your coronary or not coronary, your carotid sinus, you have all these little guys called baroreceptors. And these use your stretch reflex, like we were talking about with muscles, to basically tell your body when your blood pressure is decreasing, which is actually super, super cool. So these guys are gonna go, that little parentheses guys represents the brainstem. So these guys are gonna come in here, they're gonna synapse to other nerves. These guys are the autonomic nervous system, and they are going to affect alpha-1 receptors, which, as we all know, are on blood vessels. So basically, what happens to your baroreceptors is pretty much affecting what happens to your blood vessels. And so I'm gonna give you a little scenario of how your body's gonna change this. So when you're sitting in your little chair, all your blood is like chilling, it's going around, going to your feet, whatever, you're not really moving. However, when you stand up, all of your blood is gonna be pulled down by gravity, obviously, because we all live on Earth, we all know what's up. So all of that is going to go down. So if blood's going down, then the baroreceptors are not being stretched as much, which decreases our cardiac output, which decreases action potentials to the brainstem. So it tells your body, hey, there is not as much blood where it needs to be, so we're going to cause vasoconstriction, which is going to increase cardiac output, which is going to increase MAP. So where your blood goes and how it affects baroreceptors is how your body influences alpha-1 receptors, which is going to influence vasodilation and vasoconstriction. That's why baroreceptors are super important. Everything we talk about is actually super important because our body has it, and if it wasn't important, we wouldn't have it. Unless you're independent. Next, I'm going to talk about how the kidney affects MAP. So your kidney pretty much does everything, super complicated, does a lot of things with hormones. When MAP is low, when MAP is decreasing, when MAP is not doing what it needs to be doing, your kidney is going to release into the bloodstream something called renin. Renin is going to bind to something called angiotensinogen, and it is going to change so renin is going to apply to this guy. This guy is going to turn into something called angiotensin. I think I spelled that right. Sorry if I didn't. Whatever. Angiotensin is also called ANG1. These guys are then going to go to the lungs through the bloodstream. Wow, I spelled that wrong. That's embarrassing. To the lungs through the bloodstream. And angiotensin, so ANG1, is going to be converted into ANG2 using something called ACE. ACE stands for angiotensin converting enzyme. Very straightforward. I love it when things are named like that because they're easy to remember. So angiotensin 2 is going to affect a couple of things. So ANG2 is going to increase thirst. It is going to cause vasoconstriction. And it is going to cause the release of something called aldosterone. So these are pretty systemic, pretty widespread, but aldosterone is going to affect your kidneys. And I'm just going to abbreviate it as ALD. ALD is going to cause sodium to be reabsorbed in your kidneys, and then potassium is going to leave. So remember this fact. I'm going to explain this a little bit more in my next section when I'm talking about capillary exchange. But all of these different processes and all these different enzymes are all just trying to get MAP to increase again. So again, we're just trying to maintain homeostasis. So a lot of this is just trying to increase blood volume. So when we increase thirst, we're going to drink more water, which increases blood volume. We're going to cause vasoconstriction, which increases blood pressure. We're going to release aldosterone, which is going to cause more water to be absorbed into the bloodstream. So all these things are just trying to increase MAP. So that's the RAA system. The renin angiotensin, like ANG system or something. But it's super cool how it does that. Alright. Next section, I'm going to talk about capillary exchange. Alright, so here is a capillary. These squares are going to represent cells that are outside, that the capillaries are bringing nutrients and stuff to. Here's what we call our precapillary sphincter. Here's the artery side. Here is the venous side. We have four different types of pressures that influence the movement of water in and out of the capillary. However, we need to recognize that capillaries are super permeable to a lot of things. So they can let things in and out freely, like sodium or potassium, or things like carbs, or things like amino acids. And so anything that is permeable to the capillaries is not going to affect the osmotic anything, because instead of needing more water to increase or decrease concentration, it just either leaves or comes back. And so we need things like colloids, which are super big molecules, I guess, like albumin. Albumin is a super big protein that cannot leave capillaries. And this is a guy that's going to affect, I'm just gonna leave that there, I'll talk about him in a second. But, so things that can't leave or enter into the capillary is going to affect the movement of water, and that's all we're talking about during capillary exchange. So, obviously, from this side, from the anterior side, we have blood going through this capillary, and this is going to create hydrostatic pressure. And so hydrostatic pressure is going to be at like something like 28 millimeters of mercury. And this guy is affecting the movement of water into the cell. So I'm just going to keep a running tally down here, both in and out of the cell. Oh, you also have, I forgot to draw this part, lymph vessels. So in, we have our hydrostatic pressure, which is at 28. Yeah, that guy changes based on what the sphincter is doing. Next we have albumin. Albumin obviously cannot leave the capillary, and so when the concentration gets too high, we're going to reabsorb water. But this guy for now is going, like, at a normal resting state, at homeostasis, it's going to be affecting the movement of water out. But when we're talking about albumin, oh my gosh, pause, I just looked at my notes. Hydrostatic pressure does not affect the movement of water in, it affects it out then. So there's HB, and it's at 30, not 28. Wow. This is obviously something I need to study more, so I'm glad I just embarrassed myself. I'm joking. Anyway. And so when we're talking about albumin, we also reference this as B cup. B cup, which stands for blood colloid osmotic pressure. Like I mentioned before, albumin is a colloid, and this is in the blood. So it's a blood colloid osmotic pressure. So that is the one that's at 28. So B cup is at 28. So B cup is the only thing that's going to be affecting the movement of water in at normal resting state at homeostasis. Obviously, if something changes, if we have high concentration of something, it's going to affect the movement of water differently. I'm talking about your life is normal, your body works, okay? Next, we also have proteins that live on the outside of these capillaries. I mean, you literally have proteins actually everywhere. And so this is also affecting the movement of water out because it wants to balance the concentration of proteins on the out. So where this was blood colloid osmotic pressure, we have ICOP. ICOP, not IHOP. ICOP, which is interstitial colloid osmotic pressure, and this is also ICOP. It's also going to be out here, and this is like an 8. It's not a 10, but I mean it's still affecting the movement of water out. We also have these lymph vessels, which are creating kind of a suction if there's a negative pressure inside of them, and we call this IFP, which is interstitial fluid pressure, because it's leaving, and so this is at 3. This is also going to be moving water outside of the cell, so IFP is at 3. It's going to be moving water out. And so when we tally up and find the net values of this, there's obviously more pressure that's moving water out of these capillaries, and so water is just going to be moving out. However, I mean, things can totally change. Like, I'm not gonna draw it because I've already been drawing a lot, but I mean, if you have like an allergic reaction and you have a little mast cell that releases histones, it's gonna cause all of these simple squamous cells to contract and go away from each other, so it's gonna become super leaky. And then all of this fluid is gonna leave and you're gonna get edema, you're gonna get swelling. You can also have things, so these cells are also full of proteins because proteins are everywhere. So if you break open all these proteins are gonna move out, which increases the concentration of protein in ICOP. So more and more water is gonna move out and you'll get more swelling. And so just when you, again, it's just a relationship. When you change something, it's obviously gonna change the movement of water here. But those are the 4 factors that affect the movement of water through capillaries. Capillaries are fun. I like them a lot. We're on the last section. Are you excited as I am? I bet you're not, because I am ecstatic. All right. This last section is all about red blood cells, the contents of your blood, and then how your body gets rid of blood cells. Because you make a lot of blood cells, so you need to get rid of a lot of blood cells. So if you were to get a vial and put blood in it and put it through a centrifuge, you're gonna get all the little red blood cells are gonna sit at the bottom. These are red blood cells. You have something called a buffer layer, and then you have plasma. This guy, all the formed elements are gonna be here. So formed elements are gonna be down here, so like actual cells. But everything else is gonna be in the plasma. So if we were to have a graph of plasma, it has a lot of albumin, it has alpha, beta, and then gamma units. So albumin, I'm just gonna represent with an A, and then we have alpha, beta, and then gamma subunits. So gamma globulins are like your antibodies. We have like clotting factors, we have like a ton of very, very important things in our plasma, and they are not person specific, so you can like donate them, give them to anyone, but that's what's in your blood basically. Next I want to talk about specifically the blood cells. And so they have a little biconcave shape, so I'm going to draw them like this, red blood cell. And this little guy is full of something we call hemoglobin, which is a protein in your blood. Yeah, that's pretty much it. So I'm just going to zoom in on this guy. So you have 4 different subunits of hemoglobin. You have 2, I don't think it matters what side, but you have 2 alphas and 2 betas. Each of these guys is going to contain 1 molecule of iron. So I'm going to write a little Fe in here. Fe, Fe, Fe. And then one of these guys, these are called a heme. And a heme contains 1 Fe, which can hold 1 molecule of oxygen each. So one little thing of hemoglobin can carry 4 molecules of oxygen. And you probably have 250 million of these guys in just this red blood cell. So, a long story short, you can carry a lot of oxygen in your blood, but obviously oxygen is super, super important. But you might be thinking, but Paige, you said you got rid of a lot of blood cells, and obviously you do. You make, like, I don't know, what did we say in class today? It was like 2 million new blood cells every minute, I don't know, it was a big number. But that also means that you're getting rid of a lot. And so where this happens, I think we said, did we say our spleen? It happens in our spleen. And our spleen is super cool. I didn't know that's what it did, and I don't think anyone really knows what that's what it did. I'm not going to explain like every step here, maybe because I didn't write down every step. But here is a heme, like I was saying before. Heme, here's Fe, in the middle, and then we have nitrogens all along here. I'm just gonna represent by N. That was a W, because we're all chemists here. So this guy, basically, in a two-step process, is going to turn into bilirubin. And by doing that, we convert a couple bonds into double bond oxygen, and then we also bind, and nitrogen and hydrogen together, and put them right here. Yes. So this guy goes through heme oxygen. I'm just going to read it off of my notes because I don't have this memorized. I'm sorry. It goes through heme oxygenase, which makes it water soluble, and then it turns it into biliverdin, and then biliverdin turns into bilirubin, and bilirubin again is fat soluble, and so it binds with albumin and gets transferred to your liver. I think I just drew that backwards, but that's your liver. So in your liver, bilirubin is connected to a couple of sugars, which I'm going to represent by G because it's glucose. This then is taken to your bloodstream and taken to your intestines for absorption and a little bit of changing. So we have our little conjugated bilirubin now with a bunch of little glucoses on it. I don't know if there's 4 or if there's like a specific number. But then this guy gets changed into something we call UB, which stands for urobilinogen, and something called stercobilin. This guy is brown in color. This guy, however, continues on through your bloodstream, and goes to your kidneys. Because again, like I said earlier, your kidneys pretty much do everything. And then here, it is changed. UB is changed into urobilin, which is yellow in color. And so that is how your body breaks down these red blood cells, and where it happens, and why it happens, and where they end up, and how they're excreted in the body. If there's something wrong with your liver, you're going to have traces of unconjugated bilirubin. If there is something wrong with a duct or anything else in this process, you're going to find conjugated bilirubin. Jaundice, why you look yellow for jaundice, is because you have a buildup of pretty much, you just have a buildup of bilirubin because your liver obviously can't conjugate it, and so it can't add these glucoses to it. But that is this whole section. I'm glad you stuck with it with me. I'm glad that I got finished, but thank you, and I feel really smart, and I really like this class, so thanks.